and supervised learning. And so we are getting towards more mathematical talks, so it should be exciting.
Yeah, thanks for the introduction. Not that the previous talk wasn't exciting, but I'll try to talk about some attempts people have made to formalize sort of different fairness criteria. But I'll actually end on sort of a note of caution that these criteria can't ultimately sort of pin down what fairness means. And so when David asked me to talk about optimization and fairness, I was like, I'm not sure there's that much optimization in fairness right now. But I'll mention the word feasible region just to fake it. I hope that makes people happy. So as Christoph sort of explained very nicely there, we've seen that decisions based on machine learning can wind up being unfair or perceived as unfair without any explicit wrongdoing. And I'll give one example, which closely mirrors one of Christoph's examples. So this is the Bay Area. One of you has a startup, and you want to hire somebody for your startup. Okay, so you designed this ad, for hiring a software engineer. You should probably hire a graphic designer first, but let's say you start with a software engineer for your startup. And so this is your ad, and you want to place this on an advertising network. And you're wondering who should see this ad. Okay, you want to target software engineers, and you're worried about gender discrimination because hiring in tech is very controversial, and advertising is the first step of the hiring platform or pipeline. So this is an important sort of point of contact there. And so how do we solve advertising or targeted advertising as a machine learning problem in practice? To simplify, it's something like this. You start with the features of an individual, which are denoted by X, such as your browsing history, things you've done on the internet. And in this case, I'll highlight sort of one sensitive attribute, which is gender, and I'll call that A. And that need not be explicitly sort of written down in X, but it could be highly correlated with X. Your browsing history, generally, can be used to predict gender very reliably. And finally, there's a classifier which decides whether you see an ad or not. Okay, this is an oversimplification, but let's just see there's a classifier C which decides yes or no, show the ad or not. And what's sort of the classifier trying to do? It's trying to predict whether somebody is a software engineer, because that's the group of people you're targeting. Okay, so there's a target variable I call Y, which is whether you actually are a software engineer or not. And I'll assume for this example that somehow, if you're a software engineer, you'll click on it, and otherwise you won't. So I'll identify that with clicking on it. OK, so this is the description of the problem. And you sort of ship that to, let's say, one of the big advertising networks, and you say, do this for me. And they come back at you, and they say, here are the results of your ad campaign. If you look at precision, or this is sometimes called click-through rate, that's the probability of hitting a target given that you showed an ad. Okay, so you show the ad to somebody, what's the chance that they're actually a software engineer? That's called precision, or if you identify the target with clicking, it's click-through rate. And this is what ad platforms optimize. This is how they sort of increase revenue. They optimize precision sort of relentlessly. And you might see even a plot. This is one thing they could tell you. You might see a plot like this, precision by gender. So you look at men who saw the ad, and you see that 80% of them actually clicked on it. So that's great. And also among women, actually, women who saw the ad, 80% clicked on them. Okay, so you see, this is the same value, and it seems like this is great. Okay, so your precision or your click-through rate in both groups is the same. But as Christoph explained, if you slice the data differently, and you look instead at a criterion called true positive rate, which is somehow you flip these two things around, you look at the probability that you actually do see the ad given that you're a positive instance. So given that you qualify for seeing the ad, what's the chance of actually getting a positive classification outcome? And this is called true positive rate or recall. And this is not something ad platforms look at. Does somebody have an idea of why they don't look at this?
The results are bad?
The results are bad, yeah.
Paid for.
Sorry?
They don't get paid for.
Yeah, you don't it requires you to kind of go against your model, right? It requires you to sort of do things that your model didn't suggest, to estimate sort of among the people, that it didn't show the ad, who did I leave, or, you have to figure out, you just sort of have to randomly show the ad to people and see, among the people who are actual targets, how many of them clicked on it. So it requires some form of exploration that's not currently in the sort of the ad, pipeline. But it's sort of a measure of inclusivity. It says, given that you qualify for a positive outcome, what's your chance of actually getting it? Okay. And what's perfectly consistent with the previous results is that actually your true positive rate by gender looks awful. Okay, so men who qualify get it at an 80% rate, and women who qualify get it at a 40% rate. Okay, so if you think as the positive outcome as sort of desirable, the positive classification outcome, getting into college, getting a job, seeing even this great ad. If that's the positive outcome or the positive thing you want, then this is certainly very concerning. Okay, so a couple of years ago, we said, okay, let's think about this as a kind of a criterion, a measure of discrimination. And so we formalize this, assume C and Y are binary, so the classifier and the target are binary, and say that a classifier satisfies equal opportunity if the true positive rates are the same in all groups. Okay, so it's just you want to sort of make sure that your chance of getting the positive outcome, given that your positive instance, is the same in all groups. So in some sense, there's a sense of having an equal opportunity to get the positive outcome in all groups. Okay, same true positive rate in all groups. We just sort of highlighted this as a criterion of saying, look, this is something people might be concerned about. Violations of this criterion are perceived as unfair. So let's highlight this as a criterion. And you can strengthen this a little bit, and you can say that not only do I require the same true positive rate, I also require the same false positive rate. This is if some of the negative outcome, the negative classification is harmful, you want to also make sure that or if somehow, classifying somebody a negative instance incorrectly as a positive instance, if that's harmful, you want to make sure the harm is the same in all groups. Okay, and this one actually has a very nice mathematical definition. You can just state it as a variable R satisfies equalized odds if R is independent of A conditionally on Y. Okay, so the classifier or your score function or whatever you want is independent of the sensitive characteristic conditional on the target. Okay, so
false positive means you show the ad to someone who doesn't qualify for the job.
Yeah.
Why would you be worried about that at all?
So false positive is like if you're screening for terrorists, then you don't want to be a false positive. So want to make sure, if you're at an airport, what's your chance of getting stopped as a terror suspect? You want to make sure that different groups have the same rate of being incorrectly classified as terror suspects.
Would you want both in most cases? Or
Sorry? It's again, it's a social choice, right? Like it depends on the application. There's no, there are situations where you're mostly concerned about the true positive rate. There are situations where you're concerned about false positives or both. But yeah, that's not somehow, it's not something that you can decide at generality. Okay? But notice this means that in general, your classifier R could be dependent on A. There could be a correlation between the two. They don't have to be independent. But the extent to which they correlate is sort of justified by the target. Okay, so you can only correlate these variables if actually the target is also correlated with A. And that's why they become correlated. And in terms of graphical models, I'm not sure this is helpful to anyone here. Does somebody know what a graphical model is? Okay, I don't, but it's something about the target separates A and C, so that's just a different way of writing conditional independence, and it corresponds to separation in this 3-node graphical model. Okay, good. So what are desirable properties of equal opportunity and equalized odds, which is why we thought it was interesting to highlight this. First of all, it's kind of optimality compatible. Okay, so as you're making your classifier more and more accurate, you are allowed to sort of have a perfectly accurate classifier. So if you just perfectly match the target, that's sort of an allowed solution, and you kind of don't cripple machine learning. You can always kind of allow people to try to become more accurate. And it penalizes laziness in the sense that it gives you an incentive to reduce errors uniformly in all groups. Okay, so you're not allowed to do something like, oh, I really know what a good software engineer is among men, and so I'm going to exploit that. And I don't have much data on female software engineers, so I'm going to just randomly guess among them. Okay, so this notion would actually explicitly incentivize you to go out and get better at classifying female software engineers. Okay, and I should say that neither of these two desiderata is achieved by making just the classifier independent of A. Okay, so back in the day, people often proposed this as a fairness criterion, that your classifier should just be statistically independent of the sensitive characteristic. But it actually fails to check these boxes. So There's still a range of scenarios where this is a good thing to shoot for, but in general, this is not a good criterion. I should also say that there's no such thing as fairness through unawareness. I kind of dropped this on my dropped this from my slide decks in 2015, and then this year there was a panel with experts who proposed fairness through unawareness as a solution. So I put this slide back on. Okay, so fairness through awareness is this idea of removing or ignoring all sensitive attributes. Okay, so you just say, let's just take my feature space and just remove the sensitive attribute and then do whatever I want. Okay, and this is not a good solution, typically because the other features subsume the sensitive attributes. Okay, so you can typically predict them really well from the other attributes. For instance, your browsing history. It need not explicitly sort of disclose your gender or your race, but it's very easy to predict from your browsing history.
That's the practice if you have a job application process and you ask people not to give their names and age and you say that doesn't guarantee fairness.
It doesn't guarantee fairness. Yeah, I mean, and there's certainly a tension between what's currently sort of an interpretation of the law, that you can't look at the sensitive attributes, and what every single paper on fairness would suggest you do. Okay? So every single sort of technical study of fairness has sort of come up with this insight that you can't just ignore the sensitive attributes. But yes, that's still predominantly what sort of a corporate lawyer would want you to do. So there's certainly a tension there, and I think you asked that question before, and yeah, that's a very sort of critical point, that these things are currently in a lot of tension. Yeah. Okay, so how would you achieve equalized odds or equal opportunity? This is sort of a quick technical, excursion for the optimizers. So one way of doing this, and this is the method we had in that paper, is to post-process or correct. This should be post-processing of score function, no correct there. Score function. So what's a score function? It's any random variable that's has a range between 0 and 1 and is a function of your features and your sensitive attribute. Okay, and for instance, the sort of what's called the base optimal score is given by the function, which is just the conditional expectation of your target given the features. Okay, that's sort of your best estimate of the target given what you observed. Okay, that's an example of a score function. This is typically not what you can get. This is typically hard to get, but it's kind of what's called base optimal. And so what's post-processing? What do I mean by that? You just take your score function as a black box. You don't see how it's trained or you don't retrain it. You just take it as a black box, and you're allowed to apply any thresholding to the score function that possibly depends on A. Okay, so it could depend on A. And by sort of picking these different thresholds for different groups, you hope to achieve the constraint of equalized odds. Okay, but there's no retraining and there are no changes to the score function. So given a score function, what can you do? You can plot the true positive rate and the false positive rate, the point, for all possible thresholds. So as you vary the thresholds from 0 to 1, you can get a curve of the true positive rate on your y-axis and the false positive rate on your x-axis. Okay, so these are all the points that my score function gives you for different thresholds. And this dashed black line is sort of corresponds to random guessing. This is the score function or this is kind of the trade-off, the trivial trade-off that you get from random guessing with a certain bias. Okay? And so you generally want the curve to be sort of biased away from this trivial line. You can also look at the true positive rate, or you can look at these curves by group. Okay? So you now get a RC curve for each of the groups. You see that different groups have different trade-offs that are realized at different thresholds. Okay, and this is where I'm going to use the word feasible region. So you look at the intersection of these, the interior of these curves. And why do you look at this? Well, because you want the same true positive rate and the same false positive rate in both groups. So the shaded region is exactly what you can realize in both groups. Okay, so this stuff is not realizable in one group, and this stuff is not realizable in the other group. But the shaded region are the trade-offs that are realizable in both groups. So those are the ones you can choose from. Okay, and now if you have a cost function for true positives and false positives, these are just two numbers, your cost for a true positive or your cost for a false negative and a false positive. Once you have these costs, you can just optimize over the simple two-dimensional region. You heard the word optimize? Okay. You can just optimize. It's a two-dimensional problem. It's pretty trivial. You can solve it with ternary search, and you don't need interior point methods or anything. I guess it's an interior point method, ternary search, but okay. I'm just making up things. Okay, and so given a cost function for false positive, false negatives, you can just easily find an optimal point in this feasible region. One thing we can prove about this is that it's optimally preserving. So if R is close to base optimal, if what you start with is close to base optimal without any fairness constraints, then the output of this post-processing is close to optimal among all equalized odds predictors. Okay, so if you start something that's close to optimal in the sort of unconstrained region, then you get something that's close to optimal in the constrained region. But that doesn't mean that it's necessarily good. Okay, that just means that it's sort of good in this relative sense, but it's not necessarily the right thing to do. Okay, and the alternatives to post-processing are always to collect more data and just get a better feature set and a better data set. And the other option is to achieve the constraint at training time. And this second approach has been, pursued in follow-up work by Woodworth, Gunaseka, Ohanesian, and Srebro in last year in NIPS. And the idea here is that you fix a function class H and a loss function, this should be loss function L, and you solve this optimization problem of solve the expected loss of, my predictor or my score function from this class H with respect to the target Y, subject to the equalized odds constraint. And you can probably tell that this is like a hard optimization problem, because what the heck does this constraint even mean? Okay, so they point out that this is actually NP-hard, and so they introduce a nice moment relaxation of equalized odds, which is what you get if you imagine that all these variables are Gaussian and you enforce equalized odds on a set of Gaussian variables. Then you just get a moment constraint. So you get a constraint on the covariance, the covariance of these variables, and it would read something like this. Okay, so you get this moment constraint, and this one is actually a lot more tractable. And so if you're looking for a concrete engagement point for some nice optimization problems, I suggest you look at this paper because it has some good stuff in it. Okay, cool. And I should also point out that trade-offs are necessary. Okay, so you can't just magically sort of hope to get all these different criteria at once. Okay, so if you assume the groups have different rates of positive outcomes, which means that there are more male software engineers than female software engineers. This is sort of what the rate of positive outcomes would mean in this example I gave. And you assume your classifier is non-trivial, so the true positive rate is at least 0. And it's imperfect, so its false positive rate is at least 0. So it makes some true positives and it makes some false positives. Under these general assumptions, which is kind of what you always have, you have to choose between equalized odds or precision parity. Okay, so you can either have equalized odds or you can equalize the precision values in each group, but you can't have both. Put differently, if you achieve equal precision, as in the example I gave, so your precision values are the same in each group, you're not going to have equalized odds, and you can ensure that. Okay, so ensuring equalized odds generally breaks precision parity and vice versa. Okay, so this shows that we need to resolve these things through some kind of understanding of the domain and which constraint we actually want. Okay, we can't kind of just have everything that we might hope for. Okay, so how am I doing on time, by the way? I have 20 minutes left. Okay, so this was observed by Childecheva last year. And there's a similar trade-off for score functions due to Kleinberg, Molenatan, and Ragavan. But it's in the same spirit. Okay, so people have really cared about these trade-offs. I can actually give you the proof because it's just a very simple proof. You assume that everything holds. Okay, so you have unequal rates of positive outcomes. Call that PA in each group A, 0 and 1. And assume you have equalized odds. So your true positive rate and the false positive rate is the same in each group. And assume that the true positive rate is greater than 0 and the false positive rate is also greater than 0. And without loss of generality, one of the groups needs to have at least a non-zero chance of a positive outcome. So I might as well assume that P sub 0 is greater than 0. And so given that I assume everything holds, I want to show you that precision parity fails. Okay, I have all the criteria I want and all the assumptions I want, so I'm going to show you that the last thing that's missing, precision parity, fails. Okay, so you can't have the same precision value in each group. Okay, so how does the proof work? It's proof by Wikipedia. You take any of these terms and you Google them, and you click on the first Wikipedia link, and it gives you a formula for the precision value. It's going to tell you that the precision in group A, or generally the precision value, is equal to something in terms of the true and false positive rate. And it's specifically the true positive rate times P sub A divided by the true positive rate times the base rate plus the false positive rate times 1 minus the base rate. And as you can see, if you think about it, this term, TPR is something that's fixed for each group. But P sub A varies because I assumed an unequal rate of positive outcomes. So P sub A is different for each group, right? And what does that mean? It means this ratio varies with A. It's not the same value for different A's. And so in particular, if we have equal precision, if we want to set these values equal, for 0 and 1, group 0 and 1, then the only way that could happen is if TPR is 0 or if FPR is 0. But I ruled those out by assumption. Okay? So that's it. Okay? Both are ruled out by assumption. And so these values can actually be the same for the two groups. Okay, so proof by Wikipedia is pretty powerful. There's a lot of good stuff on Wikipedia. Good. This is great. Okay. And so as Christoph already mentioned, there's been this COMPAS debate, this ProPublica article, and it really boiled down to this trade-off. Okay, so ProPublica's main charge was that black defendants experienced a higher false positive rate, and North Point, the creator of these COMPAS scores, came back and said, well, wait a minute, we know that, and it's a corollary of our score satisfying precision parity, roughly. Okay, so North Point was correct in asserting that if you have precision parity, you can't have this. But still, ProPublica said, this is unfair. What are we going to do about this? Okay, so you're going to have these trade-offs, and to help you visualize these trade-offs a little bit better, a couple of years ago at Google, we built a tool to visualize some of these fairness trade-offs. So if you go to research.google.com/bigpicture, you'll get to a visualization, interactive visualization that lets you explore these things and get a feeling for why certain things are just mutually exclusive and you can't have them, and how different thresholds affect sort of the utility that you get and the constraints that you can hope to get. So what we've seen, yeah. In principle, it would be easy to modify to do that, but we didn't do that. So it has a fixed sort of generative model that you can explore. But yeah, we've been meaning to extend it to other scenarios and data sets that you can upload. It would. I suggested this as a course project for my fairness class, and the students were like, "Is that publishable?" And so, I guess it's not. You can't publish it, so it's not going to happen. Good. So what we've seen so far, let me summarize. So there are these formal fairness criteria or non-discrimination and discrimination criteria that people have articulated. And there are trade-offs between these and other classification criteria. And certainly as computer scientists and technical folks, we can study how to achieve them and how they trade off. Okay, so we can now go off the deep end and just sort of prove more and more trade-offs and approximate versions and how to optimize these things and all that stuff. Okay, so it seems like it's all great. But there's actually a fundamental issue that we noticed when we were working on this, which is that all these criteria that we've seen so far are observational. Okay, what does observational mean? I'm going to make it precise in a moment, but intuitively, it just means these are sort of passive observations about the world and the distribution, the data that you have right now, and there's sort of no what-if scenarios or interventions. You don't sort of consider things like, what if I change the police force allocation? How would that change my data? Maybe that is the problem, right? Maybe I should collect more features and see what happens if I collected more features. Maybe it's not just Corvettes versus Priuses, but I should actually look at additional things like where are they parked and what time of the day it is, and maybe I should change the data I have, right? But there's sort of no experimentation with the environment in this passive view of the world. Okay, and this leads to inherent limitations. I'm going to tell you. So what's an observational criterion formally? A criterion is observational if it's a property of the joint distribution of the features, X, and your sensitive attribute A, your classifier C, and an outcome Y, or the target variable Y. So in other words, practically, an observational criterion is anything you can write down as a probability statement involving only those 4 random variables. Right? And certainly everything I wrote down was just a probability statement with some identity of probabilities involving these 4 random variables. Okay, in particular, I even only used A, C, and Y. I didn't even use X. But you can throw in X and you still have what's called an observational criterion. Okay, does that make sense? People have a sort of, at this point, people are usually like, what is a non-observational criterion, right? What is something that is not this, right? And so we're so sort of used to this point of view that it's hard to imagine something that's not this, okay? But let me tell you why this is insufficient or insufficient for resolving, questions of fairness conclusively. And I'm going to tell you that, in fact, there are 2 scenarios with identical joint distributions on these 4 random variables, but completely different interpretations for fairness. And this is kind of this tension between sort of social interpretation and technical criteria. Okay, so I'm going to give you 2 scenarios where sort of our discourse on these 2 scenarios would be very different. Our sort of opinion on these things would vary greatly. But technically, formally, they map to the same joint distribution over these 4 random variables. So any observational criterion you can write down is not going to distinguish between these 2 scenarios that human beings will find very different. Okay, so let me tell you what these scenarios are. And they go back, actually you mentioned a few of those points before. So let me tell you what the first scenario is. Okay? So in the first scenario, there's gender. And gender influences whether you are a programmer or not, or whether you become a programmer or not. There's certainly like some correlation between, gender and being a programmer, being a software engineer right now. So in this probabilistic graphical model notation that I don't know what it means, you can draw an arrow from A to Y. And I guess Avi can tell the audience afterwards what these arrows mean. But so basically the way I read this is that, A sort of, you could even like think about it as sort of causal in a sense that, gender sort of influences whether you become a programmer or not. And I've also heard that if you are a programmer, you like to go to github.com and, submit pull requests and things like this. Is that roughly true? Do I have any programmers here? Okay, but I hear github.com is great for programmers. So if you're a programmer, you might go to github.com. And this becomes my first feature. Okay, so X1 is my first feature, whether you visited github.com. But there's a second feature, which is whether you visited pinterest.com. This is X2. And who here visited Pinterest in the last year? Okay, people are messing with me. This was the Stanford, I call this the Stanford effect. People were noticing that I was going to make the point that, Pinterest has a female bias. So all the men raised their hand to like mess up my point. But basically, it's still true that Pinterest has a significant sort of female bias and there are more female visitors than men. So in principle, I can sort of use Pinterest as a proxy for gender. Okay, so I'm also going to look at Pinterest. And so what's the optimal predictor going to do, the base optimal predictor, if you will? It's going to look at both of these features and it says, well, certainly I'm going to use github.com because that's like clearly predictive of programmer. But I'm also going to be sneaky and I'm going to say, well, look, if you visit pinterest.com, that makes you more likely to be female, which makes you less likely to be a programmer. Okay? So it's going to have this like indirect route of like inference where it says, I'm going to go through this proxy to like adjust my estimate or my prediction of whether or not you're a programmer. This is what the optimal predictor would do. The optimal equalized odds predictor would say, well, wait a minute, I can't actually use Pinterest because this is not separated from the sensitive attribute by Y, right? It's directly connected. But github.com is separated from A by Y. So there's this chain here, right? So it's separated by Y. So I can still use github.com, the directly predictive feature, but I can't use the proxy. Okay, so in this scenario, most people would say, well, what equalized odds is doing is pretty reasonable. In particular, it doesn't use the proxy. It doesn't use gender. It seems like a pretty reasonable thing. Whereas this one's a little bit sneaky, right? You would probably, if you had to scrutinize this, you would say it's actually using a proxy. And based on that proxy for gender, it's like adjusting its predictions. So in this scenario, this one would be sneaky. This would probably be like even legally defensible or defendable, and this probably not. Okay, scenario 2, the following is true. Again, you have gender, and you have the target variable programmer. But now there's a chain from gender through to programmer that goes through whether or not you obtained a CS degree. And so basically what this chain means is that I assume that conditional on obtaining a CS degree, you're equally likely to go on to become a programmer, whether you're female or not. But you're less likely to obtain a CS degree in the first place if you're female, at least as of today. And so there's correlation between A and Y, but it sort of goes through this variable CS degree, which kind of explains why there is this bias. And there's a second feature, whether you've been to the Grace Hopper conference. I'm not going to ask again because people know where this is going. But basically, this is again something that has a female bias. So I could again use X2 sort of as a proxy for gender. And let's look at what the optimal constraint predictor, the optimal unconstrained predictor is doing. The base optimal predictor. In this scenario, it would only use X1. Okay, why would it only use X1? Somebody who actually understands these arrow notation, this arrow notation would be able to tell me why the optimal predictor in this scenario would not use X2 or A. Avi.
On the spot?
Yeah. Because you know the arrow notation.
Not well.
Okay, not well. Okay, so if I understand this arrow notation correctly, it basically means, look, A and X are disconnected from Y by this node CS degree. Okay. So given CS degree, you learn nothing about Y that's not already in CS degree from these variables. Okay, so that's what this graphical model means. Given CS, these become irrelevant for the purpose of predicting a Y. Okay, so the optimal thing would not use them because they're useless given CS. On the other hand, the equalized odds predictor would actually say, well, wait a minute, CS degree is not disconnected from A by Y. Okay, right? There's this direct link here. It's not disconnected. It's not separated by Y. So I can't actually just go and use X1. That's not okay. I need to sort of actively correct the bias that's in X1, the gender bias in X1. And well, how do I actively correct the gender bias in X1? I need to explicitly look at A, gender, and kind of subtract things out to make things cancel. Okay, so the optimal equalized odds predictor here would be a little bit contrived, and probably people would argue with it. It would kind of explicitly use gender to kind of remove some gender bias in X1. Okay, so in this scenario, it's kind of reversed, right? So most people would be fine with the optimal unconstrained predictor. In fact, legally, this is probably what you want to do in this case. And the optimal equalized odds predictor would actually do something that is a little bit weird. It would explicitly use gender to adjust the thresholds. Okay, and that's something people would maybe not feel comfortable with.
Are there laws that tell you to not use gender or race as some predictive features in your model?
Sorry?
Are there actually laws in place that tell you to not use?
Yeah, that's sort of the interpretation of it.
Why do you say that the optimal unconstrained predictor might be okay legally?
Right, so this is sort of, here's a feature. Well, so somehow the law doesn't explicitly resolve what you should do here, right? It's just there's an interpretation of it, which, lawyers would be able to tell you about, right? And yeah, they would, not want your predictor to directly depend on either the sensitive attribute or a proxy for it. So if they find out that you say Pinterest as a proxy for gender, they would also say, well, you can't do that. And here you could probably make a case that this is directly relevant for your prediction task, and it doesn't, directly use A.
Well,
Yeah.
your intention isn't what's important, right? If you have effective discrimination, then you can still be sued.
That's right. That's right. So this is why I'm saying this is an interpretation, right? This is what, people think you should do on legal grounds to protect yourself from, disparate impact down the road or issues, claims of discrimination, which I don't think would be what it accomplishes, right? So I agree there's currently, sorry?
You're kind of in a catch-22. You can't use the protected class to make sure you're not.
Totally, yeah. So right now there's like an open tension between what, formal criteria would suggest you do and what currently the practice of, or the interpretation of the law suggests you do. It's an open conflict. It's certainly true. And not just with this notion, like anything people have proposed along the lines of fairness would be in conflict. All right, and so what you can prove about these scenarios is they actually admit identical joint distributions, so no observational criterion can distinguish them. And that's pretty shocking in some sense, because it says, if you were okay with the optimal predictor in one case, then by any observational criterion, you would also be okay in the second case. Right? And the same for equalized odds. So, I think there's really these two scenarios are very different, and you probably, we could go on and talk about them for a long time, and we're already getting into this discussion. They seem very different to us, but no observational criterion can even distinguish them at all, right?
So by observational criterion, do you mean that you don't observe what features the classification mechanism is using? We cannot observe any of those.
No, you do. You do. You observe the whole distribution, everything. You have the entire joint distribution of all the features, all the, the predictor. You can even have a white box. It's not about not observing something. You observe everything. That's why it's called observational. You observe the entire joint distribution. And these two things map to the same joint distribution, even though they're socially very different. All right, so let me wrap up because I'm running out of time. So we're curious, what is formally different about these scenarios, and how can we resolve the indistinguishability? And so in recent joint work with folks from the Max Planck Institute in Tübingen, we actually came up with a causal framework for reasoning about discrimination based on sensitive characteristics. And the paper is very much along the lines, let's entertain for a moment the idea of using causality to resolve these issues. Where would that get you? Because it's not necessarily saying this is what you should do. It's just starting to explore that avenue of research. What happens if you frame this problem of non-discrimination from a causal perspective. And I don't have time to go into it, but basically the role of causality, in my opinion, is that it shifts attention to understanding the data and its generating process. Okay, so causality in some sense, it requires you to make strong assumptions or have strong insights about how the data is generated. So not just the distribution that you observe, but actually how it was sort of mechanically generated. Okay? So it's a little bit like physics. You need to understand your domain to proceed, right? And so that can be used to articulate things like interventions and sort of what-if scenarios, and that can mitigate limitations of some observational criteria. But I should say that causality is certainly not always practical. Would you agree with that statement? Okay.
Sure.
Okay. So okay. But I kind of came to like that it's not always practical. Because maybe, machine learning is not always the right thing to do without a causal understanding of your domain. Maybe we shouldn't just blindly apply, machine learning to everything that comes across and, just squeeze everything into this prediction paradigm. Maybe in some cases, we actually want a substantive understanding of the domain before we proceed, right? And causality kind of directs your attention to that part or to that problem. So in conclusion, I would say that observational criteria can help discover discrimination or point you into sort of things that are going to be perceived as unfair, but they're insufficient on their own. So don't accept a conclusive claim of fairness or unfairness based on observational criteria. I just don't think that's what they're there for. And again, I should also say that fairness criteria are meaningless if your variables are poorly defined or measured. If your target variable is poorly specified, like instead of rearrest or instead of committing a crime, you use rearrest, which is heavily biased. All these criteria become meaningless, okay? So we need to understand about the definition of the variables that we look at and how they were measured. And that's going to reveal a lot of issues, which are also not captured by observational criteria, okay? And so ultimately, I don't think that any of this is going to replace human scrutiny and expertise. And to me, it's more about how can we come up with formal mechanisms that highlight issues to human experts in the right way? How can we guide and support human experts in understanding these problems? Cool. And so, the causal framework can help to articulate some of these problems and organize assumptions that we can make. And I think it's useful in that regard. As for concrete technical problems, I don't really have much. But, better optimization algorithms for achieving observational criteria, such as equalized odds at training time, I think is an interesting direction. And trade-off results for approximate criteria. So instead of having these exact things, you ask, what if I relax them? What kind of trade-offs do I get? I think these are two very concrete and reasonable problems to study. As for broader research directions, we can explore the space of causal analogs of observational criteria and see how they trade off. I think that's completely wide open. And I want to understand how we can utilize weak qualitative causal information. let's say social scientists tell you, well, I think this variable is causal for that, but they're not going to tell you exactly how the data was generated. They're not going to give you a structural equation model for your data. How can we utilize that to make our insights more robust? And one thing that I've been working on, which I'm particularly intrigued by, is sort of temporal dynamics, which is, suppose there's some criterion you want to achieve in the long run. What is kind of the near-term intervention or near-term constraint that we should design to get that desired long-term outcome? So rather than thinking about this problem as kind of a one-shot thing, you set up your prediction problem and it's over. You think about it as a repeated process, something that's applied over and over again. And then you draw the distinction between constraints that you place on the predictor and long-term criteria that you want to achieve. And that leads to an interesting distinction that's currently missing in the area, and a lot of new technical questions. All right, I think that's all. That's all I got. Thanks.
Can you give an example of how you did these how you put causality into this in one of those examples that you gave? So.
Yeah, so in these examples, basically you can interpret all these arrows as sort of causal, like, links in a causal graph. Like you can basically create a formalism that, allows you to basically, if you have like a link like this, some node, let's say CS x1 goes to y, you could actually flip this value, right? Like if you have a chain like this, A, you could actually say, what if I make people study CS against their natural inclination? Okay, so I set x1 to 1, right? So I divide this room into two groups, and I force, one of the two groups to study CS. So you might have to go and study CS. Maybe that's what you already did. I don't know. But go back to school, study CS, see what happens, right? So it allows me, a causal graph allows me to actually sort of entertain these what-if scenarios. Okay, so what if I inserted a certain value for this variable, and I sort of looked at how this affected things downstream. And that's basically formally what causality boils down to in this setting. And that's a more powerful mechanism because it's really, it allows you to look at things, that don't happen by themselves. It allows you to sort of break natural inclination. People behave the way they are, but causality kind of lets you consider, these interventions that you don't get if you just observe natural behavior.
But I still don't know why women don't study computer science.
Oh yeah, sure. No, and sort of, this link is very delicate, right? Like sort of, one of the weaknesses of causality is that, if you wanted to turn this into, causal, or a structural equation model, you would actually have to think about how this variable x1 is sort of generated from A. And that's certainly, I don't know, right? And social scientists are not going to tell you, right? And so there are a lot of ways for causality to go wrong because we don't actually know how, sort of what the causal link is between gender and CS, right? And so it leads to a whole nother range of problems that, you create a stronger formalism that requires you to make, in some sense, much stronger assumptions. And it's not necessarily clear how you can get to that point, how you can have enough understanding of your domain to really write down these things.
So are you saying that you must make these interventions in order to be able to do descriptions of causality? I had the impression that there were some systems of these arrows such that you could infer causality just observationally. Is that? Yeah,
so there's a lot of literature on, when can you infer causal links from observational data. There's like a set of established conditions and ongoing work. And so in those cases, you don't necessarily need to make those assumptions. You might, be able to infer it from the data you have. That's one possibility. Maria.
I was confused about one thing. So in the problem where you couldn't, distinguish between the wasn't the graphical model directed in that case as well? So you were also using a directed graphical model? It
was a directed graphical model, yeah. No, it does not, right? So a directed graphical model just kind of describes the independence, conditional independence information. That's all it does. And conditional independence is a property of the joint distribution.
Oh, so it's not a distinction between undirected graphical.
No. So like a directed graphical model is a property of your joint distribution in the sense that the only thing it encodes are independence assumptions, conditional independence assumptions.
So same as undirected. So the direction.
Same as undirected. It gives you like a little bit more sort of information about how things would factor, I guess. But it's not causal. A directed graphical model is not a causal model. A causal model makes stronger assumptions. Yeah, more questions.
Okay, so I guess a lot of your framework depends a lot on interpretability of the model that we're talking about. Like, you might imagine, right, a scenario where someone sells the bright idea to the TSA to use some deep net to do facial classification. It just happens, to pick out people with darker skins and beards to fall out to the side. So how would you take this sort of very non-interpretable models and maybe do some post hoc thing and fit them into your...
So for starters, all of these observational criteria are black box, or the ones I mentioned. So those certainly apply. And that's one good thing about them is that they apply even in those black box scenarios. And you can use them to kind of probe these black box models to see what's going on, right? Yeah, if you wanted to then go and come up with a causal model for your scenario, that's pretty hard to do, and like especially for when your inputs are pixels, right? It's kind of hard to do causal analysis based on that. Yeah.
So the equal odds, it can kind of, I guess, be interpreted as matching the distributions of the score functions conditioned on the protected class. So kind of the proportion of people at any threshold of protected class A that are classified as true or likely to default or whatever is similar to the proportion of people of protected class B that are likely to default. Is there some kind of similar interpretation in terms of distributions for equal opportunity?
So I'm not sure I completely understand the question, but I think first of all, equalized odds is conditioning on the outcome, right? It's looking at the positive outcomes and the negative outcomes in each group, and comparing distributions across that variable. Right? So it's not conditioning on the protected attributes, conditioning on I guess it's conditioning on both, but I think the important part is conditioning on the target variable, which is also what equal opportunity does. It's just that it only looks at the positive group, the positive outcome group, and not the negative outcome group.
So wouldn't it make sense to say if, for example, Facebook wants to filter out fake news, but they don't want to target conservative posts versus
right.
liberal posts, or liberal posts versus conservative posts, or whatever.
Right.
So you could say that, okay, well, at whatever threshold we use, we want to make sure that a similar proportion of liberal posts are classified as fake news as conservative posts.
Yeah.
So that doesn't qualify as equal odds or equal opportunity.
It certainly does. That's just what it is, right? You would say that, you may make your predicted attribute, whether it's, conservative or liberal, and then you would just say your target is, being, let's say, unfiltered, like being shown, and then you want that good content in each group has legitimate content in each group has the same, show rate. So that would just be equal opportunity.
That would be equal opportunity. Yeah. Okay, so I guess then my question will be flipped. Then is there some kind of distributional interpretation of equal odds?
Yeah, I don't know what you mean by that, but there is. I mean, it's just this conditional independence thing, right? To me, that's a distributional interpretation. I guess I don't understand the question.
I guess when I say distribution, I mean as your threshold varies, but I guess I can ask.
Yeah, let's take it offline. I'm probably slow to get it. Thanks.
We'll reconvene at 11 after a short break.